Hello everyone, this is a run through the materials topic questions from the Year 1 A-Level Physics workbook. So the suggestion is that you get a copy of the workbook, print it out, have a go at the questions under timed exam conditions, and then when you've had a really good go at the questions and a really good think about them, you can watch this video, which is a run through, the idea being that you get a bit of explanation of how to do each question rather than just relying on understanding the mark scheme. That little bit of insight can then be helpful in helping you to understand what the examiner was looking for, and it can help to build up your capability to tackle the harder questions in A-level physics. So question 1 on the materials section. Part A, define the density of a material. So density equals mass divided by volume, except mass per unit volume or the ratio of mass to volume. Part B. So we're given here that brass is an alloy of copper and zinc and consists of 70% by volume of copper and 30% by volume of zinc. We're given densities of both copper and zinc. So determine the mass of copper and the mass of zinc required to make a rod of brass of volume 0.8 times 10 to the minus 3 meters cubed. So we're going to use mass equals density times volume. To find the mass of copper, it's going to be density of copper multiplied by the volume of copper, which is 70% of the volume of the brass. So 0.7 times 0.8 times 10 to the minus 3. That's the volume of the copper that will be in this. So that gives a mass of 4.984 or 5.0 kilograms to two significant figures. So that's the mass of copper. The mass of zinc, similar method. So mass equals density times volume. So density of zinc, 7.1 times 10 to the 3, multiplied by 30% of the volume of the brass rod that we want to make, 0.3 times 0.8 times 10 to the minus 3. That gives us 1.704, which equals 1.7 kilograms to two significant figures. B part 2. Calculate the density of brass. So density of brass is the mass of the brass divided by the volume. So the masses we've just calculated as copper 5 and zinc 1.7, add those together, and divide that by the volume, which is 0.8 times 10 to the minus 3, given in the question. So that gives us 8,375 or 8,400 kilograms per meter cubed. Okay, so on to question 2. So the lorry is on this platform pushing down the spring. Given the mass of the lorry and given the compression of the spring is 0.03 meters. So calculate the energy stored in the spring. So two approaches to this one. The one that I favour is to calculate the reduction in the gravitational potential energy and to assume that that energy is transferred to the spring. So the way to do that is, because there's constant force acting, we can say that work done equals Fx, the energy gained by the spring equals Fx, force times extension. The force is mg, mass times gravitational field strength, and the height is the extension of the spring, compression of the spring, we should say. So that gives us 1.2 times 10 to the 3 times 9.8 times 0.03, which equals 350 joules. The alternative approach would be to use the equation. Energy stored by a spring equals half Fx, and you just get half the value that we got here. 1 mark if you've used F equals mg to find the weight, and 1 mark for substitution and 1 mark for the final value. The reason why I think I prefer the method on the right here is because there is, in this situation, a constant force, which is the weight acting down. And the energy transfer to the spring is the reduction in gravitational potential energy. And alternatively, if you have used the equation energy equals half Fx, it's not penalised. But actually, the half F is where the force is changing. In this case, the force is constant. So, 3 part A, tensile stress definition. Stress equals tensile force divided by cross-sectional area. And tensile strain, strain equals extension divided by original length. So if you didn't get the word tensile, in brackets here, or the word original, then you can still get the mark. You still get 2 marks. And the third mark is for tensile and original being used. For part B, so we're talking about a wire being suspended with a load attached, the extension being measured. They're measuring Young modulus of the material. 2 more quantities must be needed. So we know Young modulus is stress divided by strain. So we're going to need the force and the cross-sectional area. We're going to need the extension and the original length. Which measurements have they not made? So they've not made the original length measurements or length of wire, and you do that with a ruler with millimetre divisions or tape measure. So one mark for original length, 1 mark for ruler. Quantity 2 is the diameter of the wire, so not cross-sectional area. I think the actual measurement that you would make is the diameter of the wire. Method of measurement, micrometer or micrometer screw gauge to give it the full name. You take repeat measurements in several places and find an average. So there's a possible 4 marks for B, and there's 7 possible marking points there. For part C, sketch below a graph showing how the stress and strain are related for a ductile substance and label the important features. So we know initially we've got a straight line here. We can just say that that's linear, or we could call it elastic in that section. This is where Hooke's law is obeyed, so any of these things would get you that mark. And then this section is where the material is undergoing plastic deformation or exhibiting plastic behaviour. So we'd label that section plastic. These are the 2 things that you need to label. Question 4. So extending a rubber cord, and we are we're plotting a force extension graph for increasing the force, and then we are removing the load that's added all the force and plotting a force extension graph as we decrease the force. And you can see with rubber you get this difference between loading and unloading. A part 1. Give a reason why the graph shows the rubber cord does not obey Hooke's law, so extension is not directly proportional to force, or the line is not straight. So we know that if it was following Hooke's law, we'd have on a force extension graph we would have a straight line. Part 2. Give a reason why the graph shows the rubber cord does not exhibit plastic behaviour. So it returns to original shape when the force is removed, therefore elastic, or there is no permanent extension. Part 3. What physical quantity is represented by the area shaded on the graph between the loading curve and the extension axis? So just being careful what we're talking about here. So it's the area under this line, which is the loading curve, and it's sort of shaded in grey here. It's not the area between the 2 curves. That would represent something different. So area under a force extension graph represents energy. So in this case it's energy transferred to the rubber, or it represents the work done on the rubber when stretching. B. Describe with the aid of the diagram the procedure and the measurements you would make to carry out this investigation. Quality of written answer assessed. So we need a diagram showing how the cord is attached. It's fixed at the top to show that it has an original length here, and we're adding weights of known masses, known weights to the cord, which is stretching it, and we're getting an extension which we would label E here. So there's marks for a diagram, there's possible marks there. And what would we say? Well, we'd measure the length of the unstretched rubber. We'd add weights 1 at a time to stretch the rubber. At least 7 masses are added. we'd measure the extension for each weight added. This is the loading extension. We'd remove weights one at a time and measure the extension. This is the unloading extension. The extension is calculated from the length minus the original length. So it's actual length with the weights on minus the original length of the rubber cord. I'd suggest just having a look at the mark scheme as well, although I think I've covered all the main indicative points here. So question 4 is a graph question, plotting a graph of stress against strain using the data in the table. So this is straight from the mark scheme. So suitable scale on both axes, such as that shown here, e.g. not going up in threes, just keeping it simple. 1 centimetre equals 1 unit of strain, for example. So if you've got points plotted correctly, 5 or more points plotted correctly, within half a small square, that's 1 mark. And the line drawn in correctly, so the line is straight up to at least a stress of 2.5, although you can probably go up to about 3.2, I think. And then the curve is smooth beyond the straight section, so you can see how this curve is drawn in smoothly. It's not a series of sort of zigzag lines. So you need to get the line, all parts of the line, to get that 3rd mark for the line. Part B, usual graph to find Young modulus of the metal. So we know Young modulus is found from the initial straight section of the line here, from the gradient of that line. So we're going to take values off the graph and find the gradient. So 3.2 times 10 to the 5. Stress divided by strain of 3 times 10 to the minus 3. Good idea to actually draw the lines on here. That gives 1.067 times 10 to the power of 8 pascals. Answer is 1.1 times 10 to the power of 8 pascals to 2 sig figs. Answers in the range 0.9 to 1.1 are accepted. For part C, we are calculating the minimum cross-sectional area required for the rod. So we are rearranging our equation. So Young modulus equals stress over strain. So Young modulus times stress equals strain. Strain is force over area. And then rearranging that in terms of area. So area equals force divided by Young modulus times strain. So we're going to calculate the strain separately here, or you could put extension over length in to the equation if you wanted to. So you can get a strain value of 3.33 times 10 to the minus 4, which then goes into the equation over here. So force 10 times 10 to the 3, that's our 10 kilonewtons, divided by Young modulus, which we're given 1.9 times 10 to the 11, multiplied by the strain value we calculated, 3.33 times 10 to the minus 4, gives 1.58 times 10 to the minus 4, which is 1.6 times 10 to the minus 4 meters squared to 2 sig fig. So 1 mark for the correct rearrangement or substitution. So 1 mark for correct rearrangement, 1 mark for correct substitution of values, and 1 mark for the final value. Question 6. A manufacturer of springs tests the properties of a spring by measuring the load applied each time the extension is increased. The graph of load against extension is shown below. A. State Hooke's law. So Hooke's law is where force is proportional to extension, or we can write F equals Kx for this first mark, up to the limit of proportionality for the second mark. Part B. Calculate the spring constant K for the spring, state an appropriate unit. So use of K equals F over X. Reading off values, 33 divided by 0.029 equals 1137.9, or 1100 newtons per meter to 2 sig fig. Values in the range 1100 to 1200 are accepted. Part C. Use the graph to find the work done in extending the spring up to point B. So this is area under the graph method. You can see the graph, I've done that, breaking it down into two sections. And the first section here, find the area of that section. Triangle, so it's half fx, gives 0.462 joules. And then the area of this section I calculated to be 0.6 joules, and then we're going to add those two together to get the value of work done, which is 10.6, which is 11 joules to 2 sig fig. So 1 mark for actually attempting an area under the graph method, 1 mark for calculating, adding those values together, and 1 mark for the final value. You can do an individual squares method here, where each square would be 0.001 Newton meters, and then multiply that by the total number of squares. There are various ways of doing it. If you've arrived at an answer which is close, then I think the mark will be given. Part D. Beyond point A, the spring undergoes plastic deformation. Explain the meaning of the term plastic deformation. So the material undergoes a permanent stretch. That's all you've got to say. Or does not return to original length would be an alternative. Part E. When the spring reaches an extension of 0.045 meters, the load on it is gradually reduced to 0. On the graph above, sketch how the extension of the spring will vary with load as the load is reduced to 0. So we've got to draw a line back from point B to a point on the x-axis. And just to show you, so coming back from point B is going to be a line which is parallel to our initial line here, and it's going to hit the x-axis somewhere about here. So there's a range of acceptable values within the blue range, which is 0.05 to 0.02, is 1 mark, and then there's a second mark if it's within this red range, which I'm just going to check is between 0.01 and 0.014. That's the narrower range, which you get the second mark for. Okay, part F. Without further calculation, compare the work done by the spring when the load is removed with the work that was done by the load in producing the extension of 0.045 meters. So the total work done by the spring when the load is removed is less. We know that because the area under the graph is smaller. And that's one way to think about that. The area under the graph represents the work done. So if it's a lower line, then there's less area underneath. Question 7. Part A. Two of the boxes in the table. Tick 2 of the boxes in the table to indicate which are properties of the material from which the wing is made. So breaking stress is a property of a material. Young modulus is a property of the material. Stiffness constant depends on the sample, so it's going to depend on the dimensions of the sample. The material, of course, will be a factor, but it's not the only factor. The tensile strain and tensile stress are just whatever forces are applied and how the material is responding for that particular force. So they are applied values. B. Below is the stress strain graph that the engineer obtains for the aluminium alloy. So the engineer has labelled a point Q on the graph. This is the point beyond which the behaviour of the material undergoes, the behaviour of the material changes irreversibly. State the name for this point. This is the elastic limit. Use the graph to determine the Young modulus of aluminium alloy, show you're working. So we know that its Young modulus is found from the gradient of the initial straight section. So we're going to have to take value of stress and read off the value of strain, and then do stress divided by strain to find that value. So it's 300 times 10 to the power of 6 divided by 0.04 is one pair of values, equals 7.5 times 10 to the power of 9 pascals. Allow a range of values between 7.4 and 7.6. So one mark here is for 7.5, the second mark is for the 10 to the power of 9. It's easy to miss the fact that it's 300 megapascals on the stress axis, so that's why this 10 to the 9 is given as a mark here. Part C. The engineer who carried out the experiment to obtain the stress strain graph decided to stretch another sample to a strain of 0.1. She then gradually reduced the stress to 0. Show by drawing on the graph how you would expect the stress to vary with strain as the stress is reduced. So we would have a straight line starting from the line at strain 0.1 and sloping back towards 0 strain, cutting the x-axis at 0.045 to 0.055. So it's going to start from 0.1 here, and it's going to be a straight line, not like mine. This is tricky to do on a graphics tablet, but anyway, a straight line that comes back down here and cuts the x-axis between 0.045 and 0.055. Probably 0.05 is the middle point there, which would be the most accurate. So it's going to be parallel to the initial gradient. Okay, part D. Calculate the volume of 25.0 kilograms of the aluminium alloy. You're given the density there. So that's just a case of doing a volume equals mass divided by density calculation. 25 divided by 2.78 times 10 to the 3 is equal to 8.99 times 10 to the minus 3. Meters cubed, allow 9.00 times 10 to the minus 3 meters cubed. Part E, 1.28% of the aluminium alloy's volume is copper. Calculate the mass of pure aluminium needed to make 25 kilograms of the aluminium alloy. So we've just calculated the volume of the alloy, 8.99 times 10 to the minus 3. So we're going to need 98.72% of pure aluminium of the volume of the alloy. So it's 0.9872 times 8.99 times 10 to the minus 3 equals 8.87 times 10 to the minus 3 meters cubed. So that's just finding the volume of pure alloy needed. And then we're going to find pure aluminium needed, sorry. We're then going to find the mass of the pure aluminium, which is density times volume. Density we're given, multiplied by the volume we've just calculated, and that gives us 23.962, or 24 kilograms to two significant figures. So in this question, you're using the previous value calculated for volume in part D, and so you can allow an error carried forward. If you've done everything else correctly using your error carried forward value, then you can get the 2 marks for this question. So that's now the end of the materials topic questions run through. So if you have the workbook there, you can also refer to the exam board mark scheme, and do go back and have another look at any questions that you found tricky, have another go at them, and you'll see that you will be improving. So thank you very much for your participation, thank you for watching, hope to see you again soon. Bye for now.